crucifying it again. Stop.
People just want knowledge. Same thing. Maybe people
I'm
important.
so down to watch an IRL stream of this too.
You see it?
It's good.
All right. What did we do in the last class?
And
I guess Paul can teach, you'll do better.
Coulomb law application.
Coulomb's law, that's the main thing, right? You did Coulomb's law and you could actually find out the force between charges, and you also did some complex kind of questions where you had to take the vector resultant of the two forces and then find the net force. Did we do, yeah, I think I gave you a problem with the,
You didn't finish
Yes,
it.
square. Did you finish it?
No.
No, did you finish it?
We stopped.
I don't know, I stopped, but you should have continued.
I tried it, but I think.
Okay. I'll work that out here and then we'll go on to the next step. So, I mean, you can have a square where you have charges placed at different places, or anyway, charges can be placed at different places, and each charge is going to experience a force from the charges around it. Okay? And how we tackle it is by taking a vector resultant of. Okay? Now, give me the numbers. It's a square. And what was here?
Negative 20.
Negative 20 microcoulombs here,
10,
plus 10 microcoulombs, plus 40 microcoulombs, plus 30 microcoulombs. And my question was to find the force on this. Find the force on the 40 microcoulomb charge. So find, let's call it F40. Okay? Find the force on the 40. Now, what we need to do before we start finding out the net force on 40 is to find the individual what are the distances?
0.5.
0.5 each. And so before we find the net force, we have to find the individual forces from each charge. And then, so first thing is, think logically, what is going to happen to this in the presence of this? Oh, it's getting pushed which way? To the right. Call it F10. F10 means like F due to 10. And then this one is going to push it which way? Upward. So let's call it F30. And what is this one going to do? Pull it or attract, and so it's going to pull it this way. So it's going to pull it in this direction along the diagonal. So it's going to pull it like this, and let's call it F20. Now we need to find the resultant of all these three forces. If you can find the resultant of all the three forces, that's it. That will be the force on the 40. Okay. So let's find the forces individually. What is F10? F10 is the force on the 40 microcoulombs due to the 10 microcoulombs. And so use the formula K, Q1, Q2 over R squared, D squared. So K, Q1, 10 micro, Q2, 40 micro. Remember, I'm not going to take the positives and negatives and all that. I'm not bothered about it. Divided by D squared, which is 0.25. Is that right? D squared is 0.25. This is 0.5 squared, which is 0.25. You can simplify that and keep it. I will just take it as 400, so it's 1,600, right? K micro square. I leave it like that. I leave the K micro square as it is. I don't want to pull in everything and make it complicated, so I leave those things as it is. Now, what is the force on the 30? Do the same thing. K 30 micro times 40 micro divided by 0.25. And that's going to be equal to 1,200, so it's 4,800 K micro squared. Leave it as it is. Now find out this. To find out this, we need the distance. The distance is diagonal, which is 0.5 radical 2. So this distance is going to be 0.5 radical 2. If you square 0.5 radical 2, what do you get?
What, yeah.
How much is that? 0.5.
Yeah.
Right?
Yeah, it's 0.7.
0.5.
Yeah.
Yeah. 0.5 radical 2, the whole square. So 0.5 squared is 0.25 and radical 2 squared is 2. So we have 0.5. Okay? Is everyone on the same track? 0.5 radical 2 squared becomes 0.25 times 2, which is 0.5. So we are squaring, we are finding out this force, which is going to be equal to K 20 micro times 40 micro divided by 0.5. And that works out to be, that is 800, so 1600 K micro squared. Now I've got the forces, not in terms of newtons, but in terms of some kind of quantity. But I'm not going to worry about the K micro square at all now. I'll just almost take it out of the scene. I'll focus on those numbers alone and find the result. And at the end, I'll just introduce those just like that. You know, it's like 1,600 newtons, 1,600 newtons, 4,800 newtons, something. And then when you process it, you get newtons, right? So I'm going to keep a K micro square as it is, because if you want to put all those numbers, it will become messy. All right. So now we have these three forces, 1,600, 1,600, 4,800, and the angle between this is 45 degrees because it's a square. So I'm going to draw this. Now it's a problem of force diagram, you know, the resultant force thing. So we have the force here, 1,600. I'm not calling it anything, okay? 1,600. And there's a force upward of 4,800. And there's a force along the diagonal here of also 1,600. So I have three forces, and the angle here is 45. And I want to find the resultant of the three forces. So let's call this force A, force B, force C, and then you know what you're going to do. You've done that last year. We split it into horizontal and vertical components. This is a kind of review for even the things that you've done last year. So how do you find the resultant of each one? Vector, horizontal component, vertical component. That's called vector A. What is the horizontal component? How much is horizontal component? 1,600. Everything is along the horizontal. And what's the vertical component? 0. Do you remember doing all these things last year?
Yes.
Good. You should be able to pull out any of those concepts to work and solve our problem. That is not a topic that you do and throw away. You have to keep all the talents, mathematical steps and tips. B. B is that force. What is the horizontal component? 0. There is nothing horizontal. Everything is vertical for that. So it's 4,800. And then coming to C. C has two components. And the two components are, there is a component of C that way, and there is a component of C that way. C can be resolved into two components. One component of C is along the x-axis to here. The other component is along this direction. So to know how much is this, use that little, yes,
Yeah.
just volume number. Yeah.
You,
What is
use
this?
the cosine and sine, and
Yes.
they would both be 1,131.
It's 1,600 cosine 45, and this is 1,600 sine 45. They're both going to be the same. So, how much is the horizontal component?
It's 1,131.
1,000.
131.
Is it all okay? All okay? It is negative. Don't forget it. Good. It is negative because it's in the backward direction. See, it is all along the negative x-axis. It's not in the same positive x-axis direction. So this is positive x direction, but this is in the negative x direction. So we have to take that negative sign into account. Now, what is the other component? Also 1131. And is that negative? That's also negative. So put that negative sign. So we have this component of 1,600 negative. This is also negative. It's in the third quadrant. So both are negative. Now once you have resolved each of those forces, just add them up. Add this with this. And what do you get? 469. And this one? 3,600.
668.
So 3,669, and here is 469. So now we have the components of the resultant. We have the components of the resultant. Now what do? Take those components onto that diagram and draw it. Horizontal component is 469, which is still here. That's the horizontal component. And the vertical component is 3669, which is still here. Find the resultant of those two. So now you complete the rectangle, and that is going to be your resultant, the overall resultant. So what's the resultant of these two? You have to do that. Pythagorean theorem. So our resultant is 469 square plus 3669 square, the whole radical, and how much is that? You get it? How much is the result?
I get 3,698.6.
Okay, 3,699 is the result. Now is the time you bring the k micro square. Now you bring the k micro square because you already found the answer. Now you want to know the exact answer. So now bring the k micro square. Oops. Now what is k? 9, 10 power 9. Micro is 10 power minus 6. Work it out. Tell me what you get as R. The resultant is 3699 times 9 10 power 9 times 10 to the power of minus 12. Which is how much?
33.
That's 33?
Yeah.
33 newtons. Now it's in newtons. See, when you put all those variables in, now it is actually in newtons. But before that, it was in k micro square, or we kept it as it is, and we proceeded. And this way, you don't mess things up. You understand what I'm saying? You can actually multiply k micro square here itself and get it in newtons, absolutely fine. But sometimes those newton values will be like in negative powers. So in that case, your resolving becomes a little messy. But for these numbers, I think it is okay. You can still work it out. If you multiply k micro square for each of those, you will get it in newtons, and then you can do this in newtons straight up. But this is one way of doing it. This way you won't have negative powers and all that on your... Okay, so that is 33 newtons. Now I've got to find the direction. So for the direction, each direction is a resultant. The resultant is going to be somewhere here. So this is going to be pushed in that direction with 33 newtons. Right? See the force? That's the net force. So this 40 microcoulomb, if released, is going to go that way What angle? Find the angle by trigonometry. So tan of the angle is going to be equal to 3669 divided by 469. And so the angle is try working out every step. And any step you are not able to process, there is a small foundation mistake, you have to go and fix it. A small foundation mistake, you have to go and fix it.
Is it 83 degrees?
It should be 83 degrees. So which means if I release this 40 microcoulomb charge over here, it is supposed to kind of spring in that direction at 33 Newton with a force of 33 Newton. So these are all pushing it with 33 Newton in that direction, and in which direction? At 83 degrees with the horizontal. Okay? Any questions on this resultant thing? Yeah.
What was the last calculation you did? You get
The last calculation is tan of the angle is this ratio. So you find tan inverse of that. So you to find the angle, you do tan inverse of 3669 over 469. Yeah, it is. Make sure your calculator is set into degrees because we are talking in terms of degrees. Okay, so set in terms of always work in degrees, always. I don't think there's a time when you really have to work in radians. So make sure that you're setting your calculator in degree mode. Alright, all good? Put your calculators on the degree mode and then work through so you get your answers in degrees. So this is going to be 83 degrees. That's how we find the net force. Okay. It's going to move at 83 degrees only in the beginning. It's not going to go forever at 33 newtons and 83 degrees now. Because the moment it starts moving, all the distances are changed. So it will have a new force in a new direction. So you may see it's kind of taking a twist and turning around. Yeah, it's possible. It will turn around and move like that because it all depends on the net force at each and every point. And so that is what happens to a dust particle which is charged. If I have a dust particle that is charged and if I release it here, which way is it going to go? Somewhere. Because we are surrounded by charges. I am statically charged. This table has some charges. There are electrical wires up there. There are electrical wires down here. So we are surrounded by electrical charges. And so if a dust particle is here, that dust particle will experience a force due to the presence of all these charges in one direction, but it won't stay in the same direction. The moment it starts moving, it is moving away from some charges, so it will take a turn, take a turn, take a turn. So for us, it looks like random movement of the dust particle. It's kind of randomly moving around, floating around, but actually it is moving with the electric field. And that's what we are talking about now, electric field. So what is an electric field? An electric field. Electric field is something that is very similar to what we have done last year, gravitational field. Have we done something about gravitational field? What's a gravitational field?
It's just like, depending on like the object, it's the effect of gravity that it has on something else. That makes sense.
Gravitational field. Like is there a gravitational field in this room? Yes. How do you know it?
Sort of being pulled down.
Everything is getting pulled in a certain direction. If I release this marker, it's going to fall, it's going to move that way, which means it is in a field. So what is a field? It's a region around. That's it. What is a gravitational field? It's a region around a mass, where any other mass will experience a force. You get it? What is gravitational field? Does this table have a gravity? Yes. Because it's a region around the table where any other object, any other mass will experience a force. Same way here. What is an electric field? An electric field is a region around a charge where any other charge will experience a force. Make sense? Similarly, we have magnetic field. We'll talk about that later. Now, these three things are very, very similar. Gravitational field, electric field, magnetic field, they're very similar. Even in terms of equations, they are very, very identical. So knowing one of them, the other ones become easier to understand. You have done gravitational field, and you use the equations for gravitational field and all that. I mean, like the force of gravity, right? You use the force of gravity equations. Now we're going to do the electric field. So what is an electric field? It's a region, it's a space around any charge. So if I put a charge here, Q, let's say positive. If I put a charge over there, then around that charge, there is a region where a force of influence is felt by any other charge. How big is this electric field?
Depends on how charged.
How big is the charges?
Yeah.
It depends on the charge. Yeah, but say that again.
Oh yeah.
Infinite. It goes on forever. How do I know if there is an electric field here? Bring a charge and put it here. If I bring a charge and put it here, and if it's experiencing a force, yes, that means it's in the field. Bring a charge and put it here. It's going to experience a force? Yeah, there's a field there. But the field is weaker. The field is there, but it's weaker. You go anywhere, the field is going to exist. And so the field, theoretically, is going to exist everywhere. So if I put a charge over here, on the moon, will there be a field because of this? Yes. But theoretically, yes. Practically, it's going to be so weak, and there are other charges that are going to dominate. Okay? And therefore, you won't feel, that this is significantly big. So the field theoretically extends through infinity, and that's why we need to learn what is the electric field strength. That's more important to us. The field is stretching to infinity. But what we need to learn here is the electric field strength. How strong is the electric field? Well, that depends on the proximity of where you are to the charge. So to find the electric field strength, let's say you're going to bring a charge here of Q coulombs. If you bring a charge of 2 coulombs, will it experience a force? If I bring a positive charge of 2 coulombs, and this is a positive charge, will it experience a force? Which way and how much? It's going to be this way. And how much is that force? The force is going to be K, Q over what will be the distance? Square. K, Q over the distance squared. That is the force. So this charge experiences a force in the presence of this bigger charge. If I put it here, it will experience a force. Now, what if I brought a bigger charge over here than Q? Like I brought twice the charge and put it here. Will it experience a bigger force? Yes, because it's K, Q, Q is a product of two charges. So if when I double the small q, it's going to experience more force. But then if you want to define what is known as a strength, you have to, you can't just bring any charge over there. You have to bring a unit charge. So just like in gravitation, what is a unit mass? How do I know there's a field, gravitational field in this room? I have to bring a mass and release it. If I release this mass, and if it's going down with a certain force, I know the gravitational field is that much. What's a unit mass? If I drop this marker, it's going to go down with a certain force. If I drop this book, it's going to go down with a larger force, right? If I drop myself, it's going to go down with 800 newtons. That doesn't tell anything about the gravitational field here because you're dropping different objects. But for definition purpose, what is gravitational field strength? The gravitational field strength is a force experienced by a mass, which is unit mass. What is a unit mass? What's the unit of mass? Huh? So 1 kilogram. 1 kilogram is a unit mass. So if I bring unit mass and drop it, how much force will it experience? If I bring 1 kilogram and drop it, how much force will it experience here in this room? 9.8 newtons. That is the gravitational field strength. We called it acceleration due to gravity, right? Because we are talking about mechanics and all that at that time. But in terms of gravitational field strength, the value of gravitational field strength in this room is 9.8 what? Newton per kilogram. Per kilogram. So the gravitational field strength in this room is 9.8 Newton per kilogram. How do you know it? How do you test it? To find the gravitational field strength in this room, I brought a unit mass and released it. When I brought a unit mass and released it, it went down with a force of 9.8 newtons. Right? And that's why we say the field strength is 9.8 Newton on every kilogram. So the gravitational field strength is 9.8 Newton per kilogram. The unit of gravitational field strength is Newton per kilogram. You can also write it as 9.8 meters per second square. But writing meters per second square and Newton per kilogram, they seem to be different, but in terms of units they are same. But no one will write meters per second square when the statement is gravitational field strength. When it says acceleration due to gravity in this room, yeah, 9.8 meters per second square, that is appropriate. But if it is saying, what is the gravitational field strength in this room, then you don't say 9.8 meters per second square. It doesn't make sense. Say 9.8 Newton per kilogram. In the same manner, let's talk in terms of electricity. If I brought a charge of Q coulombs and released it here, it's going to go that way with a force of KQQ over D squared. Now how do I find the electric field strength? What do you have to bring? A unit charge. So take this off and bring a unit positive charge. That is 1 coulomb. Now you already know this 1 coulomb is such a huge charge. It's not anywhere near this charge, maybe theoretically. 1 coulomb is a huge one, but for unit purposes, we still have to take 1 coulomb as a unit charge. So we say 1 coulomb. So bring 1 coulomb and put it here. Will it experience a force? Which way? That way. And what do you call that force? That's called the electric field strength. We symbolize with a different letter, E. And some books write draw an arrow on the top to indicate that is a vector quantity. Just to indicate electric field is a vector quantity, it has a direction. And what is that electric field? It is a force between this and this. So it is K, Q, and 1 divided by D squared. See what happened to the small q? Small q is gone because it's just 1. So the electric field at any point in the presence of a bigger charge is E is equal to K compared to the previous equation, F is equal to KQ over D squared. You can see if I divide both sides by Q, I'll have force over Q is equal to KQ over D squared. And so you can see force over Q is the electric field strength. So what is the definition of electric field strength? It is the force per coulomb. You get it? Force per coulomb. And write it down. Just write it down. Electric field strength at any place or at any point in a space. Electric field strength at any point in space is electric field strength at any point in space is the force experienced by a unit positive charge when placed at that point. The electric field strength at any point in a region or space is a force experienced by a unit positive charge placed at that point. So it is the force per coulomb. What's the unit of electric field strength? Because I said it's force per coulomb. What is it? Newton per coulomb. What's the gravitational field strength unit? Newton per kilogram. See the comparison? You see the comparison there? Gravitational field strength is Newton per kilogram, 9.8 Newton per kilogram. And here we're calling it something Newton per coulomb. Very similar between similar units, similar equations even. In gravitation we have this equation G m1 m2 over d squared. That's what the equation is in gravitation. Here we have A q1 q2 over. So the unit is Newton per coulomb, and so E is F over Q. If you cross multiply, we have F is equal to QE. F is equal to QE. How can you use this equation anywhere else? If you know the electric field strength at a certain spot, and if you put a charge of Q at that spot, it will experience a force of QE. You get it? How do you compare this equation with the gravity equation? Q, what takes the place of Q in gravitation? Mass.
Yes, yeah.
What takes the place of E in gravitation? G. So in gravitation we have F is equal to mg. Have you seen that equation?
Yeah.
So what is this in gravitation? Mass. What is that? It's a gravitational field strength. We never use that term, but now that you're learning something about fields, you are beginning to use it. But yes, F is equal to mg. What is m? Mass. What is g? Not acceleration due to gravity all the time. It doesn't have to accelerate. Am I experiencing a force of mg right now? I'm not accelerating. I mean, I'm not really falling. Okay, so you don't have to have that as termed as acceleration due to gravity. You can also say gravitational field strength. Okay, so F is equal to mg, same as Q equal, F is equal to Q. Similar term. Q is in coulombs, M is in kilograms. E is in Newton per coulomb, this is Newton per kilogram. So if I tell you in this room there is an electric field produced because of the presence of all those charges around, and if I release an electron over here, it will move. With what force? All you do is use that equation. What will take the place of Q? Electron charge. What will take the place of E? The electric field I give you. Any questions over here? Clear? The magnitude of the electric field is this. But the electric field always comes with a direction because it's a vector quantity. So it's got a direction and magnitude. And sometimes the electric fields are all straight lines, and sometimes they're not. Gravitational field. If I drop 1 kilogram over here, which way does it go? If I drop it here, which way does it go? Right? If I drop it there, it goes straight down. If I drop it here, it goes straight down. So these fields are equal, right? Are they parallel? Are they parallel? Is this parallel to this? They're not. They're not parallel because if you kind of continue their fall, it should go to one point which is center here. So on a small scale, we feel that this is parallel, but on a larger scale, we will see clearly the difference. If I drop this marker here, it's going down like that. If I drop the same marker in New York, it's going to go like this. Because the ground is already curved. And then there you will see a significant difference. Or if I drop the marker here, it goes like this. If I go down to the other side of the earth and drop the marker, it will go like this. It's going to go in a totally different direction. So gravitational field lines are not parallel at all. They're always like pointing to one place, which is center of gravity. They're all pointing to center of gravity. So also here, if I have a charge sitting here, it's a positive charge. Is there a field around it? Yes. And you know how to find the field strength. Now we are talking about field lines. Electric field lines. Field lines, not field line. Field lines. Now what is an electric field line? Write down the definition. Write down the definition. They are imaginary lines. They are imaginary lines drawn to represent they are imaginary lines drawn to represent the path followed by a unit positive charge. The path followed by a unit positive charge when released in the field. So what are electric field lines? They are imaginary lines drawn to represent the path followed by a unit positive charge when released in the field. Now what's a gravitational field line? We also have gravitational field lines. What is that? It is they are imaginary lines drawn to represent the path followed by a unit mass when released in the field. Right? So over here in this room, they are all pointing straight to the floor. Although they appear to be parallel, they are not parallel. They are all aimed to the center of the earth. Similarly here for the charge, how do I find the field lines pattern? All you do is bring a unit positive charge and release it. If I release it here, which way will it go? So this is the direction in which it will move. What if I brought the unit positive charge and place it here? It will be shooting itself like that. What if I place it here, then it's going to go this way? What if I place it here, it's going to go this way, this way, this way, this way, this way. Those are the electric field lines around a positive charge. Those are the electric field lines around a positive charge. What about if it was a negative charge? If it was a negative charge, you release a positive unit positive charge here, it will go this way. And if I release it here, it's going to go inward. So they're not going to be inward facing lines if it's a negative charge. So whenever you draw field lines, they are supposed to have arrow marks. Just not like these are the electric field lines around a unit, around a positive charge and around a negative charge. What if these are field lines that you draw around isolated, add that word isolated positive charges and isolated negative charges. And when you say isolated, that means that's the only thing there. Nothing else is there. Isolated. So the field lines that you drew outwards is from an isolated positive charge, meaning nothing else is around. Second drawing you drew was for isolated negative charge, which means nothing else is around there. But then that's not going to be the situation all the time. There's always going to be a neighboring charge. There's something going to be there. All right? So charges are not going to be all alone. You will find. So sometimes you may have a positive charge here and a negative charge here. And then what will be the field direction around this? So if I bring a unit positive charge and release it here, which way will it go? It will go this way. What if I release it here? It's a positive charge. If I release it here, what will happen? It's not going to keep going forever. Because as it starts moving, that is going to pull, this is going to push, so this will turn. So the unit positive charge will take a turn and go like that. The same way here, turns. Same way here, turns. So that pattern is a pattern that you'll get for two charges next to each other. These are electric field lines. What if they are like charges? The previous one was unlike charges. Let's say they are like charges. Both are, let's say they are equal and alike. then what will happen? If I release a unit positive charge here, what will happen? Will it go all the way there? Because that unit positive charge is repelled from here. When it goes there, that's also saying don't come here. So it's like, just imagine a situation where you're moving away from this danger, but then there is another danger there, so you have to move away from there also. You can't just approach it. So the unit positive charge will be going that way, and then very soon we'll take a decision to go. It will get deflected off. So why is it getting deflected in that manner? Is because at different points it will have the net force in that direction. So if I release it a little to the bottom, it's going to go like that. If I release something from here, it's going to go like that. So this is a no man's land. Nothing comes here. No electric fields there. Because that is a void in terms of electric fields. That's like a null point. It's a place where nothing comes. Electric field is zero. And around it like that. So the electric field pattern is going to look like that. What will be the difference in the shape of the electric fields if they are not equal? The charges are not equal. Then what will be the difference? Like that's a bigger positive charge, and that's a smaller one. Then what will be the difference? What do you think so? What do you think is going to be the difference in the pattern? Is that again? It won't be in the middle. Yeah, like before it was in the middle, the null point or the voided point. In this case, it's going to be more here. Away from the big one, closer to the small one. So the field lines are going to go like that. This is going to be the prominent one. That's going to be the. So the null point is going to be more close to the smaller charge. What if you have both negatives or positives? Both the negative charge, both the negative charges. Then what do you think is going to be the difference? The only difference is they're all going to be inward pointing. That's it. So it's going to be the same shape. They're all going to be pointing inward.
Is it both the same size?
Yeah. So inward pointing, just going to be the same pattern. Yeah.
I just wonder, why isn't it possible for it to be in that middle spot?
Over here,
Like, yeah, it's just like in a perfect spot.
because the net force on it is going to be equal to zero. So, which means field is zero. There's no force.
Okay, so like, that's something like, why wouldn't it? Oh, okay, so that's force. Okay.
Yeah, I mean, like field line is basically representing the force. So at one spot, it's a no man's land sort of. So, The only difference between gravitational fields and electric fields, in electric fields and magnetic fields, you have the positive and the negative concept. So you have attraction and repulsion. Whereas in gravitation, there's only attraction. There's no negative. It's always going to be an attraction. So you don't have a negative mass, all that, just positive masses. So when you have a field line in any direction, when you have a field line going like this, at every point the force is going to be in a different direction. So at this point the force is different direction. At this point it's going to be in a different direction. Every point the forces are different. At this point the force is in this direction. At this point the force is in that direction. Because they're vectors. They're changing the directions. Okay? Forces are going to change directions. And so the tangent to a point on a field line will tell you exactly the direction of the force at that point, or the direction of the electric field at that point. So the tangent to a point on a field line will tell the direction of the field at that point, because it's a changing thing all the time. So when you have a curved field line, as you saw earlier, the tangent is what tells you that. Now let's do some problems which are pretty much similar to what you've done earlier, but in terms of fields, that's it. The difference is only field. So again, let's say you have a 5 microcoulomb positive charge here and a 15 microcoulomb positive charge there. Find the place where the electric field is 0. Find where the electric field is 0. In this region, not at infinity. At infinity, you can consider that to be 0, but there is a 0 in this neighborhood. So where is the electric field 0? Where is the electric field 0? Find where the electric field is 0. What are the positive charges?
Do we need the distance?
Oh yes, you should ask me.
What's the distance?
Tell me in terms of x. Okay, that's the distance. X is the distance. Now you tell me in terms of x where it should be placed. If you're not given a distance, you just give your answers in terms of an imaginary distance. So where? Tell me logically, where do you think the electric field is 0? Yeah.
Listen to the 5.
Closer to the 5. So just put a spot over there saying it's here. And then what you do is write down the electric field strength from here at this point and from there at that point, and make sure that they are equal. That's it.
Can you read that?
What do you do to find the electric field? Put a unit positive charge over there. At the spot where you're intending to find out the field, put a unit positive charge. Since you don't know this distance from here to here, call it anything. Call it anything. Y. Call it Y. And then, what is this distance going to be? X minus Y. Call this Y, and that will be X minus Y. And then you're going to write the electric field strength. Okay, so the electric field strength from the 5 to here is in this direction, E5. And the electric field from there to here is going to be E15. E5's magnitude should be equal to E15's magnitude. Is that right? The magnitude of the two fields must be the same. That's how you get the null point. So what is the magnitude of the E5? K 5 micro, and the other one is +1, so we don't care about it, divided by Y squared. And on this side it's going to be K 15 micro over X minus Y squared. You can knock off all that. 5 goes 15, 3 times. So if you take the square root on both sides, we have 1 over y is equal to radical 3 over x minus y. Correct? If you take square root on both sides, we get this. Or you go by the quadratic approach, that's going to be messier. If you go by the quadratic approach, it's going to be taking more time. But this way it will be easier. 1 over y is equal to radical 3 over x minus y. And radical 3 is 1.732. So now cross multiply. So x minus y times 1 is equal to 1.732 y. So therefore x is equal to 2.732 y. So y will be equal to x over 2.732. What is 1 over 2.732? How much is that? How much is 1 over 2.732? What is the reciprocal of 2.732?
It's 1.37.
Point?
37.
So therefore y is 0.37x. In other words, 37% of the distance from there to there is going to be the place. Okay? The position y, this part over here, is 0.37 of the entire distance. 37% of the entire distance. So the entire distance is 100 centimeters, that's going to be 37 centimeters. So you can find the field strength at different points. Again, this is very similar to what we had done earlier. The previous one, what we did was, we didn't bring 1 coulomb over here, we brought in kilocoulombs. And so we had K, 5 micro, and then there was a Q also. That's all the difference. And the rest of it is exactly the same. Okay? Any questions? Good. All good here?
Oh God.
Huh?
I have a question about. So could you explain again how you know that they're supposed to be equal?
Because my question was, where is the net force 0? Net field 0. So therefore, the two of them should be equal. See, when at one point, if you have to have a net field of 0, the sum of the fields must be 0. And because they are in opposite directions, we just add them up. I mean, we just equate it. you're learning these concepts, but it doesn't mean that questions are going to be always of the same style. You have to just use your concepts and go and solve it. Okay? Don't just think that all of these questions are going to come exactly like this. No. You may have a different situation, you may have protons, you may have electrons, you may have different things, and you may have to think in terms of electric fields, net force, or whatever, electric field lines. So you have to use a concept to answer the questions, not just the problem solving exactly. Each question is going to be different. Electric field. Around, in and around charged sphere. Electric field in and around the charged sphere. So, we have a charged sphere. We have a sphere, it's charged. So, imagine there's a sphere and you just take some charge and drop it on it. Where are those charges going to settle?
Yes.
The outside. Yeah, the charges are going to be all on the outside because they push away from each other. Mutual repulsion takes them all to the outside. So outside you have positive charges. Let's say it's positively charged. So you have positively charged and so it all goes to the outside. We'll continue with this, but just a reminder to check mastering on a daily basis. I'm going to write all these things down there. Check your mastering on a daily basis. There's already an assignment for chapter 16, part 1, waiting for you. Start working on it. I think it is due by Thursday.